Have you ever wondered why, even after converting alternating current from your wall outlet to direct current for your electronic devices, there is still a subtle imperfection in the power supply? You need stable direct current for most electronics, but your wall socket provides alternating current. The reason there is ripple voltage after direct current rectification is because the process of converting alternating current to direct current using diodes creates a pulsating direct current output, not a perfectly smooth one. While filter components like capacitors are added to smooth this pulsating waveform, they do not entirely eliminate the small fluctuations. These remaining fluctuations are what we call ripple voltage. At its core, rectification involves diodes acting like one-way valves for electrical current. In a full-wave rectifier, the alternating current input is converted into a series of positive-going pulses. Imagine a sine wave. The diodes effectively flip the negative half cycles upwards so that all the voltage is positive. However, this is not a flat, steady direct current. It is more like a series of hills and valleys. To smooth these hills and valleys, a filter capacitor is placed in parallel with the load. During the peak of each voltage pulse, the capacitor charges up, quickly storing electrical energy. As the input voltage from the rectifier then starts to fall, the capacitor begins to discharge slowly through the connected load. This discharge prevents the voltage from dropping all the way to zero or near zero. The voltage gradually decreases until the next pulse from the rectifier charges the capacitor again. This continuous cycle of charging and discharging creates the characteristic ripple waveform. The faster the capacitor discharges, or the slower it recharges, the larger the ripple will be. This behavior is fundamentally tied to the time constant of the capacitance and the resistance of the load. Understanding this mechanism gives us clear ways to minimize ripple. To reduce ripple voltage, we can increase the capacitance of the filter capacitor. A larger capacitor stores more energy and therefore discharges more slowly, leading to smaller voltage drops between charging cycles. We can also increase the input frequency. A higher frequency means the capacitor has less time to discharge before the next voltage peak arrives, reducing the ripple. Finally, reducing the load current also helps. If the load draws less current, the capacitor discharges more slowly, further contributing to a smoother output. For applications requiring extremely low ripple voltage after passive filtering, we often incorporate active voltage regulators, which further stabilize the direct current output. Engineers often use a metric called the ripple factor, which quantifies the purity of a direct current supply. It is the ratio of the root mean square value of the ripple voltage to the absolute value of the direct current component. A low ripple factor is crucial in sensitive applications, such as audio amplifiers, where ripple can introduce undesirable hum, or in precision measurement circuits, where it can corrupt sensor readings. High ripple also means that more power is wasted as heat in the components, and it can reduce the lifespan of connected electronic devices. Understanding the ripple factor helps in designing power supplies that meet specific application requirements, ensuring stable and clean power delivery. Ultimately, ripple voltage is an unavoidable byproduct of transforming alternating current into direct current using passive components like diodes and capacitors. It represents the residual alternating current component that remains after rectification and filtering. By comprehending the interplay between capacitance, load current, and input frequency, we gain valuable insights into effectively managing and reducing ripple. This knowledge is essential for designing robust and efficient power supply circuits, ensuring optimal performance and longevity for a wide array of electronic systems.